Present the conference. L-shaped method. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. The L-shaped method is a fundamental algorithm in stochastic programming and optimal control, introduced by Richard Van Slyke and Roger Wetz in 1969. The name L-shaped refers to the specific geometric structure of the array of constraints in the dual linear program. The method was first detailed in the paper L-shaped linear programs with applications to optimal control and stochastic programming, published in the Siam Journal on Applied Mathematics. L-shaped method is a decomposition algorithm used to solve large-scale stochastic programming problems, particularly two-stage linear programs with recourse. It is essentially a specialized application of Bender's decomposition. The method breaks a complex problem into two parts to handle uncertainty or massive datasets. Master problem: it focuses on the first phase decisions, which are made here and now. Subproblems: they represent different scenarios or resource actions, decisions are made later after resolving the uncertainty. The process is iterative process. The master problem is solved to find a candidate solution. Cut generation: this solution is passed to subproblems. If the subproblems find the solution infeasible or suboptimal, they generate cuts, linear constraints, that are sent back to the master problem. Feasibility cuts, used when a first stage decision makes the second stage impossible to solve. Optimality cuts, used to refine the approximation of the expected cost of future decisions. Convergence: the process repeats until the upper and lower bounds of the solution converge within a specified tolerance. The image shows an L-shaped problem defined by Van Slyke and Wetz. Since the problem is defined for two periods, the shape of the L is evident. Van Slyke and Wetz presented the formulation for the stochastic programming problem. As it is a dynamic model, the type of matrix that is most used is the triangular one, which accumulates effects from the past that can be used to project the future. This case discusses the process flexibility, where a plant can produce different types of products to mitigate the risk of mismatches caused by uncertainties in demand. The long chain design, proposed by Jordan and Graves in 1995, has proven capable of achieving the highest level of production. However, when systems are asymmetrical or when the response dimension is considered, the long chain design may not be the best configuration. Therefore, the problem of flexibility of process design in more general contexts is modeled, considering both balanced and unbalanced systems, with asymmetric plants, considering the response dimension. The problem is formulated as a two-stage stochastic program that is solved by an adapted L-shaped method, combining it with several improvements. According to the authors, it was not until 2016 that the L-shaped method was used to solve the problem of process flexibility. The effectiveness and efficiency of the proposed method and the improvements are evaluated. Process flexibility, also known as mixed flexibility and manufacturing flexibility, is defined as the ability to manufacture different types of products in the same production facility at the same time. Without the right flexibility, there would be a mismatch between capacity and demand, which could further hurt the performance of companies. Such an example can be found in the economic crisis and high gasoline prices in 2008. Overall vehicle sales declined, and consumers preferred to buy small, new, energy-efficient cars rather than pickup trucks or SUVs. Consequently, many automakers in Detroit, without flexibility in processes, suffered severe losses. On the contrary, thanks to their ability to produce different vehicle models in at least one plant, Honda and Toyota survived and even increased their market share. Motivated by their work at General Motors, Jordan and Graves introduced the concepts of limited flexibility, a plant producing only a few types of products, also called partial flexibility or sparse flexibility, and chaining. The figure illustrates three different types of flexibility. Dedicated design, where each plant can produce only one product. Long chain design, where each plant can and can only produce two products, and total flexibility, where each plant can produce all products. Due to the expensive investment in flexibility and high performance of the long chain design, it has attracted a lot of attention. However, it works well in special environments such as in balanced and symmetrical systems, and when only the demand deficit is considered. To achieve a flexible process design, Jordan and Graves propose the following guidelines for process flexibility design. Try to equalize the number of plants, measured in total units of capacity, to which each product in the chain is directly connected. Try to equalize the number of products, measured in total units of expected demand, to which each plant in the chain is directly connected, and try to create a circuit, or multiple circuits, that encompasses as many plants and products as possible. Rushchinsky, U., and Grossman summarize decomposition-based methods for solving stochastic programming problems, including Bender decomposition, also known as the L-shaped method, nested decomposition, augmented Lagrangian decomposition, subgradient methods, stochastic decomposition, and disjunctive decomposition. Among these methods, L-shaped method has become the most widely used approach to tackle stochastic programming problem because of its ease of implementation. It has been proven that the method finitely converges if the second stage function is either a finite convex function or identically negative infinity. With finite realizations of scenarios, the stochastic problem can be reformulated into an extensive form, namely, deterministic equivalent problem, DEP. The block structure of DEP is appropriate to be decomposed into a master problem, MP, and subproblems, SP. At each iteration, MP is solved without second stage variables and then first stage solutions are passed to the second stage. Solutions for the second stage generate optimality or feasibility cuts which will be added to MP to eliminate infeasible or non-optimal solutions at the next iteration. The algorithm terminates once optimality criteria are satisfied. The models included in the implementation are presented below. The PFD problem is a natural two-stage decision problem. In the first stage, strategic decisions are made prior to the resolution of uncertainty. Then in the second stage, after demands are observed, tactical decisions are made to allocate limited capacities to demand based on the first stage solution. Let the value function Q be the objective function value of each specific scenario subproblem. The PFD1 first stage problem can be formulated as shown in the image. The PFD2 first stage problem can be formulated as shown in the image. For any solution of PFD1, there always exist feasible solutions for PFD2, that is, the problem has complete recourse. It is assumed that demands follow random distribution with known mean and variance. Up to this point, a two-stage stochastic programming model with binary variables only in the first stage for the PFD problem has been developed. The deterministic equivalent problem is presented, which is the core of the model. To convert such a problem into a set of multiple deterministic problems, in 2002, Slyke et al. Provide a technique called sample average approximation to handle large-scale, or even infinite, scenarios which may be necessary for solving PFD1. The DEP problem is solved by a Bender's partition scheme and must be decomposed into an MP master problem and a DP subproblem. The multi-cut version of the L-shaped method consists of the following main steps. Step 0. We put the upper bound UB equal to infinity, and the lower bound pound equal to minus infinity. Set the number of iterations to 0. Step 1. Solve the master problem, MP. Step 2. For each scenario solve the dual problem, DP, for each scenario. The objective function of MP is equivalent to that of DA, where S is the sample size and theta is an estimate of the value function of the second stage problem with a specific scenario S. Solving MP can obtain a lower bound for PFD1. Several enhancement techniques to speed up the L-shaped method are to be discussed in this section. Multi-cut version of L-shaped method generates many new cuts at each iteration, which increases the computational effort required to solve the MP. Therefore, most enhancements are designed for speeding up the MP solving process, including hybrid cut, trust region, approximate master, warm startup, and cut strengthening. Parallel computation of subproblems is an enhancement using modern computing technology to reduce wall clock times when solving numerous independent subproblems. The nomenclature used in the experiments presented is MIP, Plex results, multi, multicut version, PC, parallel computing, AM, approximate master, HC, hybrid cut version, TR, trust region, WS, warm startup, and SC, cut strengthening. The effectiveness of the L-shaped method with different enhancements to solve the small size problems was evaluated by comparing the solutions obtained with the corresponding result of DEP. The algorithm was implemented on a standard desktop PC with two Intel or Xeon processors at 2.13 GHz and 16 GB RAM running Windows Server 8 or 2 Enterprise. By calling the optimization solver Plex 12.6, each experiment is terminated when it satisfies the stop criterion, or the solving time exceeds 3,600 seconds. The Table 1 shows the impact of sample size on objective value and differences. The differences are relative differences between two objective values of adjacent sample sizes. For instance, 1.67% is obtained by 22,626.65 minus 23,011.95. The Table 2 shows the impact of sample size on the performance of the L-shaped method and only reports the mean time to resolution, second, which represents the throughput. The result shows that the solving time increases as both the problem scale and sample size increase. Furthermore, for small size problems, different enhancement combinations have similar performance. However, when problem size increases to n.m equals 6/6, the performance of HCPCTRAM becomes much better than others. The coding presents the mnemonics of the experiments carried out. The Table 3 shows the computational efficiency of various aggregated levels. As it is shown with aggregated level being 50, the computational time decreased to 65.2 seconds while the number of iterations decreased to 19 and gap converges to 0%, which implies that, for settings April 4, 2000, an appropriate aggregated level is 50. In the following numerical studies, the aggregated level is fixed to be 50. Table shows the average computational results for small size balanced problems. It shows that, for small size problems, almost all combined strategies solve the model to acceptable tolerance level in less CPU time than MIP does, which implies that enhanced L-shaped methods are superior to MIP for small size problems. The percentage of the gap is equal to 100 multiplied by the difference in the algorithm minus the best value, divided by the best value. Overall, the HCPCTRAM experiment produces the best results. The figure shows the performance of enhancements. The combination of the HCPCTRAM improvement strategy solves problems under acceptable tolerance in the shortest possible CPU time. The bars present the results without enhancements, and the dotted line with enhancements. The single-cut version of L-shaped method performs more poorly than any other enhanced methods. Improvements aimed at solving the master problem, such as AM, TR, and WS, significantly improve the performance of the algorithm. Table 5 shows computational results for medium and large size unbalanced problems. It include average results of two medium-size balanced problems, n.m equals 8/8, n.m equals 10/10, and one large size, n.m equals 20/20, balanced problem with 4 independent instances for each. As is expected, MIP could not solve even medium-size problem, n.m equals 8/8, into tolerant gap within the given CPU time. Table 6 shows numeric study results of unbalanced systems. Here the number of plants and products is different. Again, HCPCTRAM performs best in terms of both solving time and gap. The figure presents the efficiency of cut strengthening. The figure presents the efficiency of cut strengthening. Pareto optimal cut, SC, is the strongest cut among alternative cuts to speed up the process of solving the master problem. However, to obtain a Pareto optimal cut, it is needed to solve twice the number of subproblems. There is a trade-off between the CPU time saving for solving the master problem, and the CPU time consumed for obtaining the Pareto optimal cuts. Pareto cuts was presented by Mignati and Wang in 1979. The table shows that the proposed model could get better solutions than Zhang. This improvement could be quite significant for medium to large cases. The last column indicates that the long chain structure is not the optimal solution for most experimental cases. There are mainly two reasons for the superiority of the proposed method. First, when considering non-homogeneous parameters, the long chain design doesn't always have to be the best. Second, is that the uncertainty of the demands is considered. Figure shows an example where n.m equals 6/6. LCD represents the optimal solution by Zhang et al., while HCPCTRAM is a non-long chain structure as shown in the right panel. The total cost of LCD turns out to be -25,575.58 as compared with -28,205.02 from HCPCTRAM. It shows again that the proposed method also generates sparse flexibility design, but at the same time it costs less than long chain design does. Conclusions. The problem under demand uncertainty, using a two-stage stochastic programming model, considers non-homogeneous system parameters for balanced and unbalanced systems without assuming symmetrical resource capacities. L-shaped method, an exact optimization algorithm, was used to solve the proposed model. Based on the classic L-shaped method, the single-cut version and the multi-cut version, it has been proven that the hybrid cut version, which aggregates all scenarios at a certain level between the previous two extreme levels, can help significantly speed up the solution process. Albert Einstein thought that imagination is the highest form of research. Thank you for your attention.